Hello, fellow problem solvers. They're going to be doing a number theory problem that was on an old exam that I once either made or took that I just found. So I invite you to try this nice, beautiful, very cute number theory problem out for a minimum of 20 minutes, ideally an hour-ish, but not more than 2.5 hours. If you'd like to go along with us, give it a go for the next 20 minutes really. And now let's begin. This is a very cool, easy to medium-ish type of difficulty problem. So what do we have? We have the sequence is defined by, first we have some integer, that's the beginning, and then we keep iterating this. And we need to show that the sequence will contain a square, perfect square, at some point. So let's see, how do we do this? Well, let's say an isn't a square, right? Let's say we have this is equal to some k squared plus s, where s is less than 0. I mean, it's greater than 0, but less than or equal to 2k. Okay? And then what do we have? This is going to be some an. Doesn't matter which one, but it's going to be an. And then an plus 1 is equal to what? And I write it like this because now I know what this thing is. This is k. So then this is equal to k squared plus k plus s. Okay? Now, I have two options. If s was less than or equal to k, then I'll have an plus 2 will be then the square root of this, and the integer part of the square, the floor of the square root of this will again be k. And I'll have this would be k squared plus 2k plus s. And if not, if s was greater than k, I would have that this is k plus 1 is its floor. And I would have an plus 2 would be k squared plus 2k plus 1 plus s. Okay? So now, I want to ask you here a couple of things. Do you have any ideas about what would you do next? And I think I would also add the following. If this is the case, then an minus 1, like an was formed by some number that we needed to add n to it. Like the floor of an minus 1 is either n minus 1 or is either k minus 1 or k. If it was k minus 1, then the s here couldn't be bigger than k. Because we added k minus 1 to it, and the floor was like an minus 1 was of the form k minus 1 squared plus some t, where t was less than or equal to 2 times k minus 1. So we were to add k minus 1 at most, we couldn't really get over to that point. So an minus 1 is equal to k squared plus s minus k. And now here with this couple of case-by-case analysis, I invite you to pause for the next 10 to 15 minutes and see if you get any ideas from this. What to do. And for me, the thing was, wait a second. This number is how much, in this case, how much is this number away from a square? How distant, what is its distance to its closest square? And the answer is it's s steps away. You might say, well, that was a pretty dull question. It's just s steps away. Okay. What about here? How much is it away from a perfect square? And the answer is, well, this is k plus 1 squared plus s minus 1. So it's s minus 1 steps away. Okay? Now in this case, in this other case, how much was it away from a square here? And the answer is here, it was s minus k steps away from being a square. Now, an minus 1 was s minus k steps away from being a square. But here, because s was greater than k, how far away was it from k plus 1 squared? It was k plus 1 squared minus k squared plus s, which was 2k plus 1 minus s. It was this much away from being a square. And then over here, in an plus 1, it was, just subtract the k from this, it was k plus 1 minus s away from being a square. And here it was s minus k steps away from being a square, and over here it was s steps away from being a square. Now, is any single one of these, actually is this k plus 1, this being k plus 1 minus s doesn't really add up, it's more, let's say the absolute value of this. If I haven't done anything wrong, I think, yes, I might have messed something up in the algebra actually, to be very frank with you. It was, in this step, it was much, much closer to being a square than it was in the next step. But 2 steps ago, it would have been closer. Okay. But here's where I invite you actually to pause for about 5 minutes with these distances from a square and ask yourself, how would you formalize this? For 5 minutes, just ask yourself, how would you push this towards a solution? And here's what I would do. I would say, let t be the smallest natural number in the sequence. Actually, let me put it this way. For every n, I'll make an equal to some k squared plus t. And of all the members of the sequence, let me pick the one with the smallest t. Right? Now, if t is 0, I am done. That is what I want to prove. And the smallest one exists because it's at most, like, the smallest t is going to be at most, what's it called, the difference between the 2 consecutive squares a is around. So it's a constant. It has an upper bound, and in an infinite set of natural numbers, you can always pick a smallest element. And I think, even though these are not natural numbers, if you include a 0, controversial opinion for some, but here we can say, okay, let t be that smallest thing. So we can look at now a couple of cases. If t is greater than k, can this in fact be the case? And the answer is no. T can't be greater than k because then we would have that an minus 1 would have, like, an minus 1 plus the square root of an minus 1 is equal to k squared plus t, which means this thing right here is greater than or equal to k minus 1. And then we have this plus an minus 1. So we have an minus 1 is actually going to be greater than or equal, is going to be less than or equal to k squared plus t minus k plus 1. Now, if t was greater than k, we would have this be the case, but this is not actually the bound we want. We want a bound where this is less than or equal to k plus this. And now we have this. An minus 1 is going to be greater than or equal to k squared plus t minus k. And if t is greater than k, then this is closer to k squared than t was. but I'm looking at the t such that this is smallest, where t is less than or equal to 0 and less than or equal to 2k, right? I'm looking at the t with the smallest such representation. So this isn't the fact. So we have that t is less than or equal to k. Okay. But because t is less than or equal to k, then we know that an plus 1 is equal to, we know this is k squared plus t plus k. And then we know the square root of an plus 1 and its floor is going to equal k. And then we have an plus 2 is equal to k squared plus 2k plus t. And now I know that if t is greater than or equal to 1, I'm going to get a contradiction because I have this as k plus 1 squared plus t minus 1. So now if t isn't equal to 0, I've gotten a number that is smaller than the previous one, then where was t? Which should give me a contradiction. So if t is greater than 0, if the smallest member here is greater than 0, then after 2 steps, I'm going to find a smaller one of the same form. And this is showing by extremal principle that we will be done. We picked the smallest one, we said it assumed it's not equal to 0, and then we show, oh wait, we'll pick a smaller one again. We'll get a smaller one than this. And this finishes out the problem. And I just want to show this to you because I think it's a cool little way of thinking about the problem. Maybe also we could have just gone down this route and this would have been kept decreasing and decreasing and decreasing. But I thought this way was also a cool way of solving this problem. And this finishes up, and as always, thanks for problem solving.